Okay, so chapter 7, in this chapter, we are going to talk about value function approximation. This chapter is short. We want to understand what is the concept of how we can solve the problem of memory of the Q table that we've had. So all the things that we are going to do now, basically we are trying to focus to solve the memory problem or Q table problem. Because when we multiply state and action, the table becomes tremendously big. Still we can solve many problems, not like we are disabled to solve problems. But if the state space and the action space is too big, then we have the problem of solving those problems. So in this chapter, we want to see how value function approximation can solve and can help us to deal with this problem. So in this chapter, we're gonna see parameterization of what does it mean actually, the parameterization. Then we want to later see how value function approximation for Q-learning can be defined, how value function approximation for SARSA can be defined, and how it can be defined for E-SARSA. Then we will discuss the advantage of the value function approximation. So when we are talking about the function approximation, always think we are trying to solve the Q-table problem. So as I explained, the idea challenge is that since all previous approaches we consider tabular presentation, for value function either or state action function as Q value, we have the problem of the space and the size. Because in form of the array, vector, matrices, or lookup table, whatever we do, that's very big. If it's lookup table, search inside is time consuming and big, but the speed is not the critical point here. The critical point is the memory problem, because then that can grows like terabytes of the memory that you need to do that. As I explained, state and action space for some problems can be very large and very slow to learn the value function of. We have important point here. It's very slow to learn the value of each state individually. It means that not only we have memory problem, but also that big state space and that big action space for each one of the states can be very hard that our agents see all possibilities to understand how good each one of them was. Like, let's say this is like infinity number of possibilities if I want to do path planning, and if my agent wants to visit all of those and try everything, then that's like impossible. It takes forever. That value function approximation also can be helpful for me to deal with that problem too. So we say all possible state values or Q values may not be fit in the memory that we discussed, and the solution, if we can say MDP is big actually, when state action pairs are big, of course Markov decision processes is big too, and based on that we want to find a way to parameterize the value function and remove tables. So what does it mean, parameterization, first of all? Parameterization means that, let's have a look at this, this shape over here that is representing, for example, sun. If we consider this one as target, the purple one as target, the smallest one, so parameterization means that we can write the function w sine x, that sine of x is like the form here. But w sine of x, we can put a parameter as w To find the best adjusting parameter for that, I can put 1, 2, 3, that this can give me different shapes that you can see over here. Like this is 1, this is 2, this is 3. And what I want to do, I say, okay, the target is this one. And I want to find the W to adjust this term over here to overlap and kind of find best W to fit this one. And this is called parameterization of the value function approximation that we will also discuss it, how to solve it. The objective basically is find this W over here to fit the as best one. Of course, this is sign term, very simple. Even you make fun, okay, this is like obvious. We know what to put there to achieve it. But if that is complex shape, we want to find many of those W's in different forms to find out how to have a function or how to have a approximation function that that can fit me that problem, to solve me that problem. Is this part clear? Yeah.
What is the difference between this and Fourier approximation of a function?
Louder, I couldn't.
What is the difference between this and the Fourier approximation of a function?
For what?
Fourier.
Fourier?
The Fourier series?
Fourier series.
Yeah.
Fourier series is like, their objective is almost similar. Their objective is almost similar. Here, we want to find some W parameters for the function that we have, and there also is similar. Yeah? There are different techniques. For example, here we are directly solving an equation. But for example, neural network that I'm going to discuss next lesson is like finding many of those W's for different terms to finally find the approximation function. But that can be with other techniques too. That with machine learning techniques, we can have anything that helps me to achieve it. We have the parameterization objective, but the neural network is the best one. Okay. Any other question? So also this is like this is the exactly I drawn with the 1, 2, 3 sign. You can change it. This is the true example. So we can say that we are estimating value with value function approximation, so that we usually represent it as the state value or Q value function that is in a parameterized function as the hat one. So it is kind of, I mentioned you a couple of times that in machine learning, all versions of different techniques that we are going to do, we are working with. When we have estimation, we put hat on the equation that we have over there. So here you can see Q hat, V hat. So we want to have value function approximation, we want to approximate Q or V. Value function or Q value function. Approximate it. It means that we want to throw out the table and approximate the Q or V. So how we can do that? We usually show it in this form. So it is very common to show it in this form. We can write the value pi of the state can be equal to approximately to the estimation of the value for that state and the weights that I want to find. So I'm adding the weights W's to this value pi in order to say, okay, instead of storing the value directly, having it in form of function anymore. This one was table, this one is going to be function. And this W is like similar to this sign that I just explained to you. Of course, more complex. We will see how we can find it. Is it clear? So first term is for value of the pi of the state. Here I can do the same thing for the Q value. Q of the pi can be state, as you know, can be represented as state and action pair. For each state, the actions, all possible actions, that be written as the estimated Q, that is state action, and again we have W's here. So whole idea is to find out how we can bring it to the form of W. Of course, the problem becomes more complex. Our problem becomes more complex because already we wanted to solve this. We saw Q-learning can solve this, right? We saw Q-learning can deal with this and find it. Now we are adding something else. We are adding W also to the problem. Why? Because we have memory problem. We want to deal with that too. Okay? Now let's consider that state S indicated as set of features as x1, x2, up to xn. Up to now, we didn't talk about this. Now, we also need to kind of declare what is the state. So far, I was telling we are at state T. State T added by 1. We know already. State added by 2. But now, we don't know it anymore also. Why we don't know it? Because we don't have table anymore to go look up table and, okay, say this is the state. We don't have it. So that we need to take into considerations of some features of this state. Those features can come from vision, for example. Those features can come from reading the parameters of the joints of your robot. Or anything in the environment that is important for us, the features can be considered in this form as x's, inputs. If you are already familiar with neural network, these are inputs of neural network. If you're not, we are going to discuss it, how it looks like. So that I can give you a brief glance. In Mario game, we said that we have states, actions left, right, and states where the position of Mario is. But we want to, instead of considering the position, for example, consider whole image as RGB image as input as states that we have, for example. We are moving toward make it more comprehensive to solve. It's like human vision. You see the environment, you make decision. So, if we consider a state like that, we can write linear approximation that this linear approximation can be shown in simplest form. The linear approximation for these states, for a state value function, can look like this. What does it mean? It means that value of the estimated value of the estimated value of the S and W is equal to sum of all of the n's weighted W's times the features of state. So this state has a couple of features, all of these features, that each one has some weight. Sum of all of them represents my estimated value of the state and W that I'm defining. Kind of saying that, okay, if I draw a picture for you, for example, here, let's say I can see this, your agent can see this, there is a ball, and this ball is moving in the environment, for example. Then these x's are changing, and some of all of those that can be visible for one state can indicate my estimated value. This is just the simplest form of what is happening, but of course we cannot do. We will see that we should bring the, for example, Q-learning function updating in the game, in the algorithm. On the other hand, we can do the same thing for Q. So for value, if you remember, as you remember, it was the estimation of the one state, but on the other hand, we can have the Q value that considers the action at each state, which action is the best. We can do the same. Here, just we need to consider weights of the actions times each one of the features of the state that we have. Any question? Okay. In other form, to make it more understandable, we can also represent it in this form that we can say estimated value of the SW. That is kind of, we want to bring it in this form instead of value pi of the S, can be represented something like this. What does it mean is that S is as input. We have a state that also includes some x's as input. We want to find series of w's that give me the, if I want to find the value function, I have the value of the state and w. So I want to have some value function approximation, whatever it is, doesn't matter. Is it simple, complex, whatever it is. We want to find this, put a value function approximation technique here that by giving this state gives me the value that I want. But that value comes from where? That value comes from, for example, Q-learning algorithm. That in next slides I'm gonna adopt it in. Okay? We will see how that can happen. State as input. I want to define value function approximation, put it here to find w's for me. That gives me the value that my for example, Q-learning algorithm or any technique that I've used as the reinforcement learning technique is over there. So here is not, that's not good for Q-learning. This one is better for Q-learning. So if you want to have the Q of the state action W instead of this, we have the, now instead of state, we have state and action as input. Not only the features that you can see, the action that you are running, your agent is running also will be as input. Then we want to have a value function approximation that finds the values that gives me back the Q value. It's kind of, I want to have some algorithm that memorizes the table. The simplest thing explanation is like that. This guy over here is kind of memorizing the table that I have. It's like some guy studying this table numbers, this number is that number is that, and when you asking the number says, okay, this is the number, and this is the answer over there. You give, okay, if this happens, and if the state is this, and this happens, what is the Q? And this guy says, oh, this is the Q. And that Q is the value that is in table. It's not exactly same, but very similar, because it is approximation. It's better if we can get the exact value, but I need to correct it. It's not because we cannot achieve it. If we have it, then we have overfit problem that later I will discuss with you. Then we lose the generalization. So these are the neural network and machine learning topics that who didn't study and don't know, I will go in detail. Yeah, we have to. There is no way. We have to go those complexity in order to be able to solve this problem. Okay, any question? I'm trying to break it down as much as possible. The simplest form of explanation to make it understandable. Please, if you have questions, ask. So to having value function approximation, one of the best approaches is the neural network. We can replace neural network instead of this value function approximation. But better than neural network is deep learning techniques that nowadays we have, and because neural network also has limitations if the state action is growing too much also. But deep learning techniques can also deal with very, very, very big state action space and learn also that too. So because of the GPUs that we have, that's not very hard to learn it, and that's the reason that we will try to replace it in order to achieve it. There are many papers that use directly neural network, and there are many research and papers nowadays that they are working with deep learning and deep learning with different architecture to improve that part. So now we say for state value function, if we want to show it in mathematical form of the nonlinear approximation function, we also can say, okay, now if we want to bring the neural network instead of that value function approximation, we can say the estimated value, state and w for value function can be written as g of the x and w, semicolon and w. That can be, this g can be represent neural network, for example. So whenever you see this g over here, this g over here means that we are going to put neural network over there that, based on the features that I have, finds the w, finds some weights for me, that network that I have, that the objective is to estimate the value. For this one, the other one is to estimate the q value. The same g, but here we consider the action over there too, actions over there too. So therefore, we can say that we need to somehow, if we have a network, although I consider you don't know about neural network, let's say we have a value function approximation that we want to find w's, we need to somehow define an objective for that to find those w's. That objective function usually can be shown as e of the w or j of the w. Is very common to show it in this. This e means the error of the weights. It means that I have real value, some value, some number. I have value function approximation that estimates that value. Like I have 10 here, this estimates 9. So objective function says how difference is this? How much error I have over there, simply. And we represent it as E or J of W. We will see in neural network how we can define it. I will define it for you. And here also I'm gonna define, I'm gonna bring the, for example, Q learning into the game, or SARSA or E-SARSA. So the whole idea is minimization of the objective function that also is known as loss function. Are they different? No. Loss function is same as objective function. There are multiple names too. Later on I'm going to introduce you. So wherever you hear loss, it means that you have objective function. And what is the error that you have? How much error of approximation is? I tell you, like I write a number here. Then I remove it. Then I ask you, what was that number? Then you say some number. And which one is closer? That's your loss function of the learning of what was the number. And then first time you have big error, right? Second time, if I write it, you try to memorize better. Then you improve it. Then your loss function gets improved. If I do that 20 times, 50 times, and if I tell you, if you say it wrongly, you're gonna lose some mark, then mostly you try to somehow memorize it. Then that's improvement of loss function that neural network is trying to do the same. We will see how to do that. So to write this loss function, of course, I need to define it in two steps, right? One target value and one predicted value. Target value that I've written here, and predicted value what you predicted, each one of you. And if I wanna show it in formal way, I can write the error of the W or loss of the W is equal to expected pi that includes the value of the pi value of the state subtracted by the estimated value that is coming from the weights. So the differences between target and prediction, this is target, this is prediction, becomes my loss function simply. Okay, this is prediction of the neural network. This is the value that I have. Where I have it, Q-learning, for example, solved it for me. Have found some number. The values in the table, I mean. The values in the table are like kind of this one. And whatever my network, function approximation network is estimating is this one. I get the square of the difference, like the loss, then I can write my loss function as E of the W. I want to find some good W's, kind of, to minimize it. So we can say that this is an optimization problem, and finding parameters vectors of W, like we can call it different techniques, like MSE, mean square error. I already explained how it is. I explained RMSE, that MSE is like not residual one, just MSE, and pretty similar. So that we are just finding the loss over there. So this optimization problem, now you may say, okay, finding those W's, how can I find it? How I can have value function approximation to guess those W's? Is there a mathematical way? Almost no, because if you have big complex problem, we cannot deal with it. For example, in Islam, we've seen some technique, mathematically we did that. But here, no, we don't have it anymore. In order to deal with it, there are many different techniques. One of the most famous one is the stochastic gradient descent, SGD. And this algorithm can solve it. What is it? No worries. Next lessons, I will try to explain how it is working. And during neural network, I will try to cover the minimums of the requirements in order to deal with it. So that's called a stochastic gradient descent. Maybe you know already. If you pass the neural network, you know, and that's better. You can easily understand. Now, we want to say, okay, let's a little bit talk more about how to calculate the target and predicted value for value function approximation. Keeping this loss function into mind, this is general form, just the differences of the values. How we can do that in detail, there can be multiple solutions. The most common way is using temporal differences. That these temporal differences can be coming from, for example, Q-learning technique that we've seen. So now if we want to write value function approximation, that guy over there as Q-learning, we will have what? We will have an equation like this. What is this equation? We are writing the error of the loss of the W as expected. The function over here that we have is exactly Bellman equation that except we added W weights over there. So it means that instead of solving Q table with Bellman equation, I change the equation somehow to form of loss function for value function approximation. Is it complex? No. Reward added by discounted maximum of this term over here. That exactly the same thing we learned already, but what we have additionally here, these W's. These W's, and this one is square now. New form of value function approximation. On the other hand, the objective function for updating the weights can be shown in this form. May look big, may look complex, but it is not. Let me show you why. So the weight, the W's, the objective function can be written as the learning rate, alpha learning rate, and the same equation here comes down like reward added by discounted maximum of the state and action and weights subtracted by the estimated Q. So this is estimation Q, and this is the maximum of the next states, that both are coming from estimation actually, because we have the W, we don't have Q table anymore. Instead of Q table, those come from value function approximation. That this is going to be neural network later. And most importantly, we have a gradient here. That this gradient indicates how much gradient of the update and how much importance of the update of that Q should be on the weights that I have. So to make it 100% understandable, of course, we need to go long way of understanding, for example, this estimation, how can be calculated. This estimation, how can be calculated, and that gradient, how can be calculated. In order to be able to solve this one, that we will need 2-3 lessons maybe in order to achieve that point. But anyway, just for now, consider that this part and this part over here, instead of Q table, is going to come from neural network. A network that is going to give me some numbers for this Q and this Q. That's it. And this is like maximum of Qs, right? Maximum of many. So we are going to have a network. We are asking what is the maximum of this state action? It is going to give us something. What is the maximum of that state action? We are kind of asking that network, and gives us numbers and gives us numbers, and put them back and calculate the everything for updating the network itself too. So, any question? So as I told you, the Bellman equation is important. Now you can see Bellman equation. We extend it to value function approximation based on the Q value. On the other hand, let me see what we have. Not here. The real target value. This one is in practice also prediction from model of the this model over there. That exactly comes. It means that comes from neural network. But how that is happening, of course, you need to be like completely know what is the neural network, how it is working, what are the gradient descent, how the weights, how gradient can be calculated. Then you will be understand fully what's happening over here. Then after knowing those, we just plug these together, then it works. That's it. We kick the Q table over there, put the neural network there, then that solves our problems. But yeah, that's a little bit long way to go. On the other hand, if we want to do with SARSA what we do, that's very simple. We take the SARSA equation and put it here. Instead of max, we run it on the unpolicy one. We're running on the directly what action we've chosen. That's it, simply. What if we go to E-SARSA? The same process. Instead of that part that was max, we get the sum of those. That's it. Can we write another form of Bellman equation, or we have only 3? We have many. You can also invent yourself. Then if it works better, you can publish your own paper. So these are like These are like whatever is happening over there. Now let's talk about the advantage. So far you know that we are solving memory problem because the state action is very big. This is critical first problem. Second, as I mentioned briefly, we will have generalization. It means that even if our agent doesn't see all of the possible state and actions, the neural network kind of can give us some answers that is close. It's kind of like if this is the direction that I want to go, my agent haven't tried all possibilities, just tried few. But if I ask somewhere in middle that I never seen, the neural network kind of will say, okay, this side seems to better. That is called generalization. Kind of understanding the concept. Humans do the same, right? We understand the concept of, for example, if I leave this, the gravity drops. So I don't need to try all the objects. My agent is the same. You don't need to try everything. Take the table to leave it. Maybe this won't drop if I leave it. So if your function approximation can be generalized, then we'll understand that, okay, these kind of actions is good, these kind of actions is good, and you don't need to, your agent doesn't need to try everything. It is better to try, but doesn't need to try everything. And this is very huge benefit that also we have for that one. On the other hand, if you remember, we said that we have discrete and continuous states and action spaces. What does it mean? It means that all the time that I was explaining, I said that like you consider the tail, I'm a state here, then I go to the next state. But that's not true, of course. I can go a little bit. I can go a little bit or very big state. So in continuous environment, I don't need to say exactly the discretization of the environment. Based on this implementation, value function approximation, also I can engage continuous environments and continuous action spaces into the game too. So if I want to like say my arm is like discrete, then some angles I predefine. So instead of that, you can give freedom and solve problem in continuous form. So, any question? Is everything clear? Okay, so this is the end of the value function approximation chapter. To push forward, there is no way. We have to go to see later how neural network is working first, then how, for example, gradient descent, how update of the values are working, then how generally deep learning is looking like, and I will try to cover the minimums. These concepts are one semester course basically, that if you want to learn deep reinforcement learning, you must have already done the neural network to come here and continue. I just quickly review. But basically we want to push toward advanced algorithms in this course. So I will try to cover the minimums that you need in this course. Then you will be able to understand to solve the problems. But of course, if you want, if you are eager, you must go learn more with neural networks and deep learning. What is the convolutional neural network? What are the different architecture of networks in order to develop and solve these kind of problems? So there is no other way. That's the path that we should push forward. And I highly recommend to you that when you have free time, start to study it as much as you can, but although I will try to cover the minimum requirements. Okay, any question? Clear? Good. So